All right, Chemistry 30. Class today, we're going to start into Chapter 5, talking about electrons, specifically valence electrons and bonding and different things like that. We just got finished talking about the development of the model of the atom. And we talked about how the model of the atom has been developed over the centuries from, and I'll just bring this up here real quick, from ancient Greek philosophers discussing theories of science to John Dalton, and we'll go over this assignment a little bit, maybe more in depth another time. But John Dalton, theorizing atoms as kind of solid balls, sort of thing, and each one is a little bit different for each element, and they combine in whole number ratios. Really the first experimentation on that. And then Thomson came along, and he discovered that there was a positive and negative charge. He discovered that, in his cathode ray tube experiment, that a beam of particles can be deflected, by a magnet, and in this vacuum tube. And so he theorized that there was a negative aspect to the atom, and that, as opposed to what Dalton thought, that atoms were indivisible. He thought that there are other parts to the atoms inside the atom that we need to explore, and so that was sort of Thomson's model. It's called the plum pudding model, and he thought that the positive and negative charges were just spread throughout. Rutherford came along and did the gold foil experiment, where he shot alpha particles through a thin sheet of gold foil and expected them to blow through the sheet like a cannonball through a tissue paper. But what he found was that these rather large alpha particles were deflected somehow, and even some of them seemed to bounce right back from this thin foil. Anyways, he theorized that there was some kind of dense positive region in the atoms that these particles were bumping into. And so where Thomson had thought that the positive and negative charges were spread throughout, Rutherford theorized that, I think there's kind of a small dense region in the atom that is positive, and the negatives are kind of outside of that region. And of course, if we talk about Niels Bohr, he was the one that theorized that these electrons, they travel outside of what they would call the nucleus, or the center part where the positive charges are, and they travel in strict orbits. Now that's changed a little bit, in our present understanding of the atom. However, that was a big deal, and when you see that planetary model of the atom in lots of TV shows and Letterhead and things like that, that's Bohr's model with the little nucleus and with the the electrons surrounding that. Millikan came along, and Millikan's experiment was the oil drop experiment, and he basically determined the charge of a single electron to be somewhere, really small, obviously, but I think it's about 1 × 10 to the negative 19 coulombs of charge, and that was pretty big, in the model of the atom, giving electrons a charge, and basically they realized as well that electrons have virtually no mass compared to protons and neutrons, which we sort of consider the electrons just as a negative charge and not really occupying any mass of the atom. But so that changed Thomson's model a little bit, in that that the negative charges were quite a bit well, I should say the electrons are surrounding the nucleus, and there's sort of this positive negative interaction. And let's see what else here. So when we talk about radioactivity, we're talking about nuclear decay and things like that, and Marie Curie, and radioactive decay, in that a large sort of unstable radioactive element can decay over time and become two other elements that the nucleus can actually disintegrate. And so we talked a little bit about that. And this brings us to the notes that we're looking at here now, and in Chapter 5, and we're talking specifically about the current, updated model of the atom, where electrons, are sort of seen as particles and as waves. So you get this wave-particle duality, which we'll talk about in more detail in a few minutes. But it's very, very interesting. We talk about a new type of mechanics, a new type of way of looking at how electrons behave. Um, and we find out more about the shapes of atoms and something called orbitals, basically regions of space surrounding the nucleus that electrons can occupy. And so anyway, so we kind of get into that in Chapter 5. So here are the notes for Chapter 5, and these are the notes that we've already covered in class. This is just a brief summary. But Max Planck, he found that energy is emitted in small packages of energy called quanta. Um, this is important because this is the beginning of the wave-particle duality of electrons and of energy. And so the energy waves have properties of particles. So just like a ball rolling down a hill or being thrown through space, you can actually see energy, view energy that way in some respect. De Broglie discovered that small particles, and we're going to talk specifically about electrons this chapter, moving at very high speeds produce a wavelength. So much like color it emits a frequency, or it has a wavelength. Electrons, these small things moving at very high speeds, can also produce a wavelength, and that's very important in understanding this duality of nature as well. So particles have the properties of energy, and this brought us to the wave-particle duality of nature, which says that particles can act like waves. And if you remember in the Physical Science 20 class, we were talking about like water waves and sound waves and different things like that. And it's really sort of a kind of a slushy sort of wave form. I mean, if you talk about electrons sort of behaving differently, you can kind of think of it as a as a wave instead of a particle, and there's depth and that sort of thing, and it emits radiation and a frequency and wavelength. And so it's not just like a ball rolling down a hill. So particles can act like waves, but also waves can act like particles. And so again, this is that wave-particle duality of nature. Scientists later proved this to be true, and the most important thing was that the movement of these electrons have predictable wavelengths, depending on sort of how much energy they occupy. They can exhibit certain wavelengths, and so electrons have predictable wavelengths, which give rise to our math equations that describe the behavior. The idea of a dual nature of objects began a shift in thinking from classical or Newtonian mechanics, and that's what I was talking about, just like a ball thrown through the air, or a planet traveling through space, or an apple falling on Newton as he's sitting under a tree, or whatever it is. There's rules and math equations that govern that motion, but we were discovering here, scientists were discovering that there's a new type of mechanics called quantum mechanics that talk about very, very small particles moving at extremely high velocities, and that of near the speed of light. I did also talk up here too. You see the Einstein's famous equation here. When we're talking about this wave-particle duality of nature, if we look at Einstein's equation, mass here, the m is mass, and E is energy, and notice that they are said to be equal. There's certain conditions that would make these equal. Energy has mass, and mass can be transformed into energy. And the speed of light here is the c constant, huge number. And so if you multiply a small amount of mass times this huge number squared, you get the approximate amount of energy that this could be transformed into. So we're talking about nuclear decay. You actually can lose mass in a nucleus, and that's that gave rise to the atomic bomb and the different the nuclear world that we talk about as far as weapons that is converting energy and stuff. This small amount of mass can be converted to a really large amount of energy proportionally. So that's what that is. And so that's, of course, particle, mass, wave, energy, sort of that kind of comes into play there as well. So again, Newtonian mechanics, visible objects, or rather large objects, a ball or a planet, traveling at regular velocities. And planets move pretty quick, but that's still not near the speed of light. And so that's Newtonian classical mechanics, and quantum mechanics, these small particles at very high speeds. We also talked about something called the Heisenberg uncertainty principle. You see that down here. And what that is a summary of basically explaining how when we try to observe electrons in atoms, I mean, it's obviously extremely difficult, but any time that we try to observe something, okay, especially like if we're taking a video or something, taking a video of an electron, like over here, we want to take a video of an electron, we have to shine light on it in order for us to see something. We must view the light that's reflected from it. Because an electron is so small and it's so volatile, it is greatly affected by these small packages of light energy, or the photons, that we might shine on it. Okay, and so this makes observation in a classical sense very, very difficult, because a relatively large amount of light energy is applied to this tiny little electron. And so if you think about it, the example that I gave in class here today was that if I were to blow just a puff of air on one of my larger students, one of my big guys in my class, okay, would that little puff of air make him move involuntarily? I mean, could I shove him around the room by puffing? No. Okay, that's a very small amount of force applied to a very large object. But if I had a fruit fly or something, a really tiny little fruit fly, and I blew a puff of air, on the fruit fly, I could blow it right off the page, or its path. It was flying in front of my face, and I blew on it. I would completely disrupt its path, right? And so this is sort of what we're talking about. As soon as you try and take a picture or shine a light on an electron, you greatly affect its path, and you change its behavior. And so this is called the Heisenberg uncertainty principle. It summarizes this by saying the exact position and the exact momentum, and that's the mass times the velocity, but its position and its path, or momentum it's carrying, of an electron cannot be known at the same time. That's page 112 in your text if you want to read about that a little bit more. But this is the problem. How do we take a picture, or how do we know what an atom inside of an atom looks like? Even if it were possible, how could we do that without getting a true behavior? And in comes the math here. Okay, so we can't take a video of an electron and know its true behavior. This is where Schrodinger comes in, and he decided, you know what, I'm going to treat the electron as a wave, and I am going to generate some mathematical equations that are going to govern its behavior. So instead of trying to take a picture of it, he basically tried to use math to describe what would happen to this electron. And in a series of very, very complicated equations, Schrodinger he came up with basically a single wave equation that would describe the behavior of an electron, given sort of its energy. And the behavior of an electron forms something called orbitals, or electron clouds. Now, if you think about, okay, let's say that this is the nucleus over here. This is the nucleus of an atom, and we have, an electron flying about. Okay, it's flying around, and even this little drawing that I'm drawing right here. Okay, this electron is three-dimensional. It's flying around, and you can tell that it's in totally random, chaotic, motion. But I am staying sort of within this, sort of spherical region. If you picture this as three-dimensional. This electron is staying, and that's exactly what Schrodinger said. If an electron has a certain amount of energy, it will behave a certain way, and it'll stay most likely in a certain region. And his equation showed a bunch of different shapes or orbitals that electrons could make in space. And so I'm just trying to get rid of some of this for you. And so he was saying too that if an electron has a little bit more energy, it wouldn't stay in this sort of spherical, ball-shaped region around the nucleus, but it might actually, it might swing way out here, and then go right here, almost like it gets drawn towards the nucleus and flies right by it and gets repelled. But then it's like, oh wait, there's a little bit of an attraction, and it kind of comes back. It's like a slingshot almost. I mean, it's not exactly like that, but anyways, you see what's happening here is there's a bit of a region of space that is sort of shaped like an hourglass, or like two kind of balloons on either side of the nucleus, and that's a different kind of orbital. So an electron can bump up to this sort of orbital if it has more energy, and so on. And so what I'm going to do is I'm going to get you to watch this YouTube video here. You might have to just jot that down because you can't press on the link, I don't think. Maybe I'll get that in the space below the video. But watch this link. It's a good YouTube video, and it sort of summarizes a little bit about what we've been talking about today. And yeah, it's kind of interesting. It's 7 minutes, and the last, honestly, minute or two might be sort of beyond where we want to go, but I think it's a kind of a good little video to summarize. So that's the first part of the notes for Chapter 5. I did ask that you do these questions from the textbook right down here, and September 20th may not be applicable to when you're watching this, but these are the questions I'd like you to do from the textbook, and then we'll take a look at 5.2, talk about quantum numbers next lesson. So, thanks for watching. I hope that was easy for you to understand as we kind of just sort of get into a little bit of Chapter 5 here for video number 1 on Chemistry 30, Chapter 5, Valence Electrons.